In this section of 15.2, we're looking at line integrals. This is a new type of integral called a line integral, and you'll see the integration symbol with a C. So far, we've done indefinite integrals and definite integrals in Calculus 1 and 2, and in Calculus 3, you begin with those double integrals and even triple integrals, and now we're looking at what are called line integrals. A line integral is this integration symbol with the C, where C is the smooth curve of some function of x and y ds. In this case, we're integrating over a piecewise smooth curve. Consider the mass of a wire of a finite length. Suppose this path is the shape of the wire, and the density varies. The density is given by that function of f of x, y, z. Well, this line integral will help us find the mass of a wire. This theorem shows us how to evaluate line integrals as a definite integral. What you need is a line integral in this form where you're given some f of x, y and ds, and you need a parametrization for c. You're going to then write this as a definite integral. We're on that path, the time interval is from a to b, so those are going to be your bounds of integration. In this function of x and y, you're going to replace every x in the function with what x equals on the path. You're going to replace every y in the function with what y equals on the path in terms of t. And then you'll multiply that by essentially the magnitude of this r of t vector valued function. I'm sorry, the magnitude of the derivative of r of t. So you want to find r prime of t by taking the derivative of x of t and y of t, and then you find the magnitude of that, which is your square root of the quantity of x prime of t squared plus the quantity of y prime of t squared dt. It's important that when you have a line integral, you'll notice you'll have x's and y's and even z's. But when you write this as a single definite integral, you're going to have a single variable t. So make sure that everything that's inside the definite integral is in terms of that single parameter t. Again, if you have r of t, which is a path in space, then your function could have x, y's, and z's. You would replace every x, y, and z in the function with what it equals on the path. And then again, you would take the derivative of the path and find the magnitude of that dt. And your time interval from the path is the bounds of integration. Now, if your f of x, y, z equals 1, this line integral actually gives you the arc length of that curve. So we see this in the bottom shaded blue region. The line integral of just 1 ds is equal to the definite integral from a to b of the magnitude of r prime of t dt. In this example, we're going to be evaluating a line integral. Let's evaluate this line integral over the path c of x squared minus y plus 3z ds. If you're given the path here from the point 0, 0, 0 to the point 1, 2, 1, you may need to come up with your own parametrization. Here is one such parametrization. You can let x equal t, you can let y equals 2t, and z equals t, and then your time interval would be from 0 to 1. So you're going to replace every x in this line integral with t, replace y with 2t, and replace z with t. But then this ds is going to be found by taking the derivative of each of these in the path, and then taking the square root of each of those components squared and added together. And your bounds of integration are going to go from 0 to 1. Okay, so if you take those derivatives, the derivative of t is equal to 1, the derivative of 2t is equal to 2, and the derivative of t is equal to 1. And when you plug it into this and simplify, you get the square root of 6. So going back to that line integral, that ds you're going to replace with the square root of 6 dt, and you're going to replace every x, y, and z in the function with what it equals on the path. And then again, your bounds are from 0 to 1. So now you have a single definite integral. You can then evaluate this by simplifying, bringing out the constant in front, evaluating after you take the antiderivative, and get your final answer of 5 squared is 6 over 6. All right, let's evaluate this line integral of 4xy ds over the path C, and we're given the r of t equals ti plus the quantity 2 minus tj, and the time interval is from 0 to 2. Pause the video, try this one on your own, and then come back and check your solution. Okay, let's evaluate this line integral of 4xy ds over the path C, where C is the path r of t, a vector valued function of ti plus 2 minus tj for the time interval from 0 to 2. Recall that this ds is equal to the magnitude of the r prime of t dt. Since we are already given r of t, let's calculate r prime of t by taking the derivative. The derivative of t is 1, so that's going to be 1i, and the derivative of 2 minus t is negative 1j. Now if we take the magnitude of the r prime of t, we find that by taking the square root of each of the components squared and add them together. And in this case, we get the square root of 2. So this line integral of 4xy ds can now be written as a definite integral. So that definite integral, the bounds of the definite integral are actually the time interval for the path. So our bounds are going to go from 0 to 2. We're going to replace every x in the integral with what x equals on the path. Looking at the path, your x is going to equal t, and your y is going to equal 2 minus t. So it's going to be 4 times, we're going to replace x with t, and we're going to replace y with 2 minus t, and we're going to replace ds with the magnitude of r prime of t, which we found to be the square root of 2 dt. So now we have a single definite integral. We can simplify this by distributing the 4 and the t, and that square root of 2, you can bring that out in front. So it's going to be the square root of 2 times the integral from 0 to 2 of 8t minus 4t squared. And this is a single definite integral. You've practiced this enough. You can work this out. To find this, the solution is 16 squared root of 2 over 3. So when we evaluate the line integral, we're replacing the x and the y with what it equals on the path, and we're replacing ds with the magnitude of r prime of t dt. Okay, try this one on your own. Evaluate the line integral on the path C of x plus 4 square root of y ds. In this case, our path is not given as a vector valued function. It's given simply as a start point and an end point. So we need to come up with a parametrization, that r of t. And again, there are many ways of doing this, so I'll illustrate one way. Here, you're starting at the point 0, 0, 0, and you're moving to the point 3, 9. And it's a straight path, so you can actually come up with the equation of the line using the y-intercept and the slope. Since you're going from the point 0, 0, the slope of that line here is equal to up 9 over 3, or that we could say the slope of that line is 3. So this equation is y equals 3x. You can introduce the parameter. You can let x equal t, and then if you let x equal t, y would have to equal 3t. And if x is equal to t and y is equal to 3t, we can use that as our parametrization. which is equal to r of t. Let's look at this. R of t is equal to your x of t, which is that's going to be your ti, plus your y of t, that's going to be your 3tj. We do need a time interval here. The time interval for your start to end. If you plug in t equals 0, you begin here at the point 0, 0. And then if you want to make it all the way to this point 3, 9, your ending point is going to be t equals 3. Ending time interval is t equals 3. Alright, so now again that ds, we're going to replace that with the magnitude of r prime of t dt. Since we came up with the parametrization for the path is ti plus 3tj for the time interval from 0 to 3, we want to find r prime of t, taking the derivative to get 1I plus 3j, and then we take the magnitude of that. The magnitude of r prime of t is equal to the square root of 1 squared plus 3 squared, or the square root of 10. Okay, so now our line integral, the line integral of x plus 4 square root of y ds can now be written by making the substitutions. It's going to be the integral, the definite integral using the bounds of integration from the time interval for the path. It's going to be from 0 to 3. We're going to replace the x in this equation. We're going to replace the x with what x equals on the path, here or here, whichever one. They are going to be the same. So it's going to be t plus 4 square root of y, and the y, we've already defined y to be 3t. So it's going to be 4 times the square root of 3t. And we're going to replace ds with the magnitude of r prime of t dt. So it's going to be square root of 10 times dt. So now we do have a single definite integral. You can bring that square root of t out in front. It is a basic integral. You can work this out, and you will find that when you evaluate it, you get 57 square root of 10 over 2.